Okay, so let's solve another example. The example has two loops. You have resistances, you have some batteries, and the important thing to do is to label points across each element so that you can easily get the loop equations. So we want the current in each resistance. So the first thing to do is to identify where the junctions are. This is the systematic way to solve any problem. So where are the junctions? The junctions in this problem are at B and E because the current splits here. Current, say, comes in here, it splits into two parts. Here the current goes here and it splits into two parts. So B and E are where the junctions are. Now the next thing you need to do is to identify the currents, put currents in the circuit. You can put the currents anywhere you want, but they have to start at a junction and end at a junction. So always a current starts at a junction and ends at a junction. You can go in any direction, you can call them any name you want. This is a particular choice of the distribution of currents. Current I1 starts at B and ends at E, going from here to here. Current I2 starts at B and ends at E, going in this direction. Current I3 starts at E and ends at B, going in this direction. So the currents always start at a junction and end at a junction. Okay, what's the junction rule then? If you apply the junction rule, what would it be? Well, we can apply the junction rule either at E or at B. It'll give you the same result exactly. If you apply it at E, the current I1 is going in, the current I2 is going in, the current I3 is going out. So I1 plus I2 is equal to I3. If you apply the junction rule at B, the current going in, I3, the current going out is I2 plus I1. It's the same thing. So you don't get an extra equation by applying the junction rule at both points. You get the same equation. So if you have three unknowns now, we have I1 and I2 and I3, we need three equations. So the second equation, let's take the loop equation B, G, E, F, A, B. Let's see how you can do that. If you take the potential at B and then you go across from B to point G, what happens to the potential? It increases by a value of 10. And then when you go from G to E, what happens to the potential? Remember, based on this choice of current, the current goes from high potential to low potential. So this point is at a lower potential than this point by how much? By 6I1. So you get minus 6I1. Then when I go from E to F, no change in potential because this is an ideal wire. When I go from F to A, again, based on this choice of direction of current, the potential here is higher than here. So if I'm going to see what happens to the potential when I arrive at A, it's lower than F by how much? By 2 times I3. So you get minus 2I3. Now, when I get back to point B, there's no change in potential from A to B. So I get back the potential B. So the potential now at this point is VB. So that means that VB plus 10 minus 6I1 minus 2I3 is VB. So you can cancel the VB and you get this equation, the loop equation. So we need another equation, and we can get that, for instance, by going VB to C to D to E to G to B. Do the same thing. The potential at B, if you take the potential at B and you go from B to C, what happens to the potential at C? Is it lower or higher than B? Based on this direction of current, the current goes from high potential to low potential, so the potential at C is lower. Lower by how much? 4I2. And then when I go from this point to this point, what happens to the potential? The potential at D, is it lower or higher than C? The negative side of the battery is facing D. That means the potential at D is lower. Lower by how much? By 14 volts. Then I go from D to E, nothing happens to the potential. When I go from E to G, when I arrive at G, is the potential larger or smaller than E? Remember, based on this direction of current, the current goes from high to low. So the potential at G is bigger than the potential at E. By how much? By 6I1. And then when I go from G to B, the potential at B is lower or higher than G. The potential at B is lower. Lower by how much? By 10 volts. So now I've arrived back at the same point, and the potential then is VB. So that means that VB is equal to VB minus 4I2 minus 14 plus 6I1 minus 10. And so you can cancel the VB, this loop equation. So now if you take those three equations, the junction equation and the two loop equations, and you solve them, you will get these results for the currents. I1 is this value, I2 is this value, I3 is this value. Now it's very important, I'm not going to show the steps, you should do the steps on your own to see how it works. During the steps, if you get a current that's negative, and let's say you got I1 is 2 and I2 is minus 3. When you come to get I3, you have to plug in the value of I2 as minus 3. You can't put it as plus 3. We know that the currents in the end, we're going to flip the directions, because the current here is negative and the current here is negative. That means that the wrong direction. But during the solution, you have to keep them as they are, the negative values that they are. When you find the final solution and you get now all the currents, then now we can start to think how to change the current and the direction of the currents to make it the correct direction. So based on this choice, this outcome of currents, current I1 is in the correct direction. It's a positive number. Current I2 turns out to be negative. Current I3 turns out to be negative. That means I3 and I2 are not the correct direction. All you need to do then is just to reverse the directions and put them in the correct direction. So I reversed I2 and I reversed I3. And now if you solve the problem again based on this direction of currents, and you can do that to check for yourself, you will get the same numbers but just with all positives.